Hi everyone, welcome to our freshwater systems. Before we start, I do want to let you guys know this is an extremely long lecture. So I'm going to break it into several different videos, and if I were you, I would not print out absolutely everything. Or if I did, I would do it as very small slides, like 6 to a page, because otherwise you're going to run out of paper and toner, and I don't want that. So anyway, jumping right in, freshwater systems. In general, before we can talk about a whole lot about water, we need to know its main characteristics. So if you remember from chemistry, and if you haven't had chemistry, please, by all means, print this slide out and make sure that you've got good notes on it. Water has a high capacity to absorb and store heat. So it has, if I were to heat up a solid, it's going to heat up or lose heat or cool down much faster than water will. Water will either, it takes a long time to heat it up, but once it's heated, it stays warm for a long time. Water is also considered a universal solvent. Most things will dissolve in water. The exception to that is nonpolar molecules like oils. And water has a very high surface tension, so I'm sure, or I hope, everybody got to do the experiment in elementary school where you put drops of water on a penny to see how many will fit on the top of a penny. And this is why water will form almost a little bubble on the top of a cup, like it won't overflow. It'll rise just a little bit above, and that's because water sticks to itself and forms this really tight surface tension. It is the only compound whose solid form, ice, is lighter than its liquid form. Water's densest form is actually at -4 degrees Celsius. Now water freezes at 0 degrees Celsius, so frozen water will float on top of very, very cold, dense water, which is why we find icebergs floating instead of at the bottom of the ocean. And probably the most important characteristic for us is that sunlight can penetrate water at various depths. Now, once we get down to the abyssal zone, we have no sunlight reaching the lower levels of the ocean, but sunlight does penetrate a good ways down into water, which means that we can have photosynthetic organisms living below the surface. It's not just within the first few inches. Those photosynthetic organisms can live a good ways down. Just to give you some perspective, we currently are facing a global water shortage, and when we run out of water, we're going to run out of food. Those two are linked extremely closely together. We're going to be looking at a moment at the global hydrologic cycle. You should have studied the hydrologic cycle or the water cycle extensively in middle school. But in general, that means that water is transferring from the atmosphere to the land, the oceans, and then back to the atmosphere. 97% of all water on Earth is found in the oceans. 2% is in ice, where we can't get it. And only 0.001% is in the atmosphere. That's the water vapor that makes up our clouds. In general, just as a general term or general number for you, we only have access to about 1% of the water on Earth. Okay? So if you haven't studied the hydrologic cycle in a long time, here's a brief simplified diagram for you. This is the water cycle. Some terms you may not know. Okay, we all know that water evaporates in heat. So here we have evaporation from lakes, from vegetation, in general, evaporation coming off of precipitation. All of this evaporation, here it is coming off the ocean, leads to cloud formation. Water evaporates and then condenses into clouds. A term you might not remember is transpiration. Transpiration is the movement of water from the roots of a plant up through the stem and then eventually from the leaves of the plant. So if it goes through a plant, we call it transpiration. Once the clouds have enough water in them, then water will form its liquid version, or if it's cold enough, a solid version, and fall to the earth as precipitation. That's snow, water, hail, any kind of water falling from the sky. Once it hits the ground, it may go into a stream, which will flow into a river and into an ocean or a lake. It may infiltrate. Infiltrate means that it seeps into the rock layers or into the soil, and there it stays as groundwater. Groundwater could go into vegetation, it could flow into a stream, it could go directly to the ocean. When groundwater goes down deeper into multiple layers of soil and then into rock, we call it percolation. So water percolates through the soil to build aquifers, and we'll look at that in just a moment. This is just an estimate of the world's water supply and how long, first of all, how much water is in different locations, but then how long water stays there. For example, water can stay in the ocean for thousands of years, but atmospheric water is usually only there about 9 days. Rivers and streams keep their water for about 2 weeks. Groundwater could be there for hundreds to thousands of years, depending on where we're looking at. A lake, usually tens of years before the water is completely recycled. Ice caps and glaciers, depending on the global climate, could stay there tens of thousands of years. And let's see here. Obviously, I hope you know this, Earth's surface water is only found in liquid, solid, or gaseous form. We don't have any strange plasmic forms of water on Earth. But the residence time we just saw can vary between a few days to thousands of years. Excuse me. The amount of water that all people and plants and animals are competing for, remember I told you, is that 1%? It's a little bit less than 1%, but it's right around there. And this is all living things on Earth are competing for that 1% of water. The more industrial production we have increases the amount of water we use. And when I, let's see here, the mass of the water we use is 1,000 times the total production of those minerals. So the amount of minerals that we make or reproduce or mine, we're using 1,000 times more water to get those minerals. Okay. Few vocab terms you definitely need. Groundwater, hopefully you gathered, is water that's below the water table. Think of the water table as like a collection area. And we'll be looking at various water tables in the North Carolina area. So groundwater is all of that water that flows into there. It is below the surface, and it only happens where we have saturated conditions in the soil. The water is going to move into the ground, or I'm sorry, the places where water moves into the ground are called recharge zones. That's where the aquifer, the water table, is recharged. When water moves out, we call those discharge zones or discharge points. So anytime the water leaves the water table. Occasionally we have places where water seeps through different pores, and those are Vedas zones, or Vedas zones. So an aquifer, I've used that term a couple of times. An aquifer is an underground zone where we can find groundwater. That's all it means. We do have, before I go there, we do have confined aquifers, which have a layer of impermeable rock, so rock that the water can't go through, sitting on top or below them. And we have unconfined aquifers, which do not have that impermeable rock. And you'll see from the model that I brought to class, we're going to go through that model, you'll see the difference between a confined and an unconfined aquifer. When I move water out of the aquifer, when I pump it out, we do form what's called a cone of depression, and that's where the land in the area will sink around that well. Okay, so this is another example of your water cycle, but it includes all of these different terms. So if I have an effluent stream, excuse me, an effluent stream typically is a discharge stream, and it will collect water coming off of here. So I've got water coming down into my effluent stream, and that's going to flow away. We also have my influent stream. Again, I'm collecting water, but this time the influent stream is able to seep down into the water table, and we have a recharge mound right here. So this is where water is entering the water table. Down here, we do have, it's labeled as an aquifer, but when I can get the water up, I make I have a well, and my Vedas zone is, it forms this little depression where a depression in my aquifer where I'm pulling water out. In general, I have effluent streams. You saw that in the picture. This is a stream that is maintained year-round. We call them perennial streams. They don't go away. During the dry season, they have seepage from the aquifer to keep them flowing. An influent stream is one that is entirely above the water table, and it only flows if I have precipitation. So these are like mountain streams that get very flooded when snow falls and melts, and then when there is no snowfall or when we don't have precipitation, then the stream dries up and goes away. And these are called ephemeral streams when they only last for certain periods of time. Any given stream can be both at different parts of it, or intermittent at different times of year. So every stream, usually we classify them as an effluent or an influent, and sometimes they're perennial and sometimes they're ephemeral, but depending on the amount of precipitation you've had and the time of year and the area you're living in, different parts of a stream could fall into either category. So surface water and groundwater. Surface water obviously is the water we find above the surface. We should be considering these the same resource. They're the same thing because they interact so closely. Nearly all surface water environments have some kind of linkage to groundwater, so we can't really separate them. If I take groundwater out of one area, it can lower stream flow or it could lower lake levels. Even more importantly, if I add pollution to a stream, it can seep into groundwater. If I have a groundwater, or if I have a leak of some sort of contaminant, and it gets into groundwater, it can lead to our surface water. It can lead to our streams and lakes. And as we saw in the Strange Days video, we can have a groundwater pollutant coming into our groundwater system that then leads to the ocean if we're somewhere near the coast. Okay, so this shows some of the interactions. If you look at one, I've got streams coming in, and number two, I've got a lovely city. So this would be a source of pollution right here. Number three, I also have a sewage treatment plant. This is where sewage from this city is being treated and then re-released into the system. Hopefully that water is clean, but occasionally sewage leakage does happen from sewage treatment plants. It depends on the kind of treatment we're doing. Number four, we've got agricultural land. So all of this, my city here and my agricultural land is draining a lot of the water coming off of this mountain. When we get down to 6, these are my suburbs hanging out here, and my reservoir. So this would be like a large lake that everything is flowing to. It doesn't show it in the picture here, but it's very likely that my city is actually getting their water either from an underground system from our groundwater, or they could be pumping it from this large reservoir. And you can see my water table is this dashed line here. This is the part of the ground that we can find water. So if I dig into this water, or dig into that ground, I can find some water. I'm going to use the U.S. as an example here, but in general, water supply at any point on the land surface depends on lots of different factors. The rate of precipitation, evaporation, and transpiration. So how fast does water enter and leave the atmosphere? And how fast are our streams flowing? How much water is flowing through them? How much water is flowing through the groundwater? We take all these three things and we take all these different factors and come up with a water budget. The water budget is a model that balances how much input we're getting and the storage of the water in our system. So same thing with your money budget. You've got money coming in. If you've got a job, you've got a paycheck coming in, you've got bills you have to pay, you have to come up with some kind of budget to make sure that you don't take out more than you're putting in. And hopefully you have a savings account where you're storing some of that extra money. In general, just a general equation you need, precipitation minus the amount of evaporation we get gives us our runoff amount. And that will add into our water budget. So in North America, we have 758 millimeters per year of precipitation, which gives us 18,300 kilometers cubed of water in precipitation. We have less evaporation, 418 millimeters a year and 10,000 kilometers cubed evaporation, which gives us about 8,180 runoff in kilometers cubed per year. Okay, so that runoff is the amount of water that is not immediately taken back into the atmosphere. Okay, so if you look, some of these are kind of funny. So take a look at this chart when you have some time, and we're going to compare the water budgets of different continents around the world.